Vigor is a grant that Vigor is an acronym in and of itself, which stands for Vertically Integrated Graduate Research and Education. Vertically integrated is supposed to mean like the vertical axis here is like levels of education. So PhD, postdocs, professors, young professors, old professors, and then it says graduate research and education. That's this acronym that the NSF came up with. The NSF is another acronym, National Science Foundation. So they came up with this acronym and to fund, and of course, they just want to fund science, right? But they have to, I think more or less, they just want to fund science, but they have to convince, they have to make it always look like they've got a new idea, right? So, and they just want to fund departments to do science and do cool science and so on. But I mean, genuinely, people do want to fund science at all levels of education and so on. So Vigor was the new idea for a while. And then at University of Georgia got 2 consecutive Vigor grants, maybe with a gap in between. I believe that's true. And so there's a bunch of money to support things, and in particular, part of their proposal was they would run these things called Vigor Research Groups, which would be targeted one semester or one or two semester long groups run by a professor focusing on particular research problems. So this is the advertised area which comes in after. Anyway, and so the Vigor Research Groups happen at PhD level, then at some point they said let's have Introductory VIGRE Research Groups, which are for undergraduates. So that's the idea. I'm gonna be running one next semester. I think we'll meet basically 1 hour a week. I believe it counts to 1 hour. And if you want to know more technical details, you can ask. I forget all the details about that, course number and all that, but your advisor, Dr. Schiffer, can help you sign up for it. I would welcome anyone who wants. What I want to talk about is what we're going to do in the group. What we want to try and produce. We want to try to produce something. So it'll be you're going to be working more than me if you join up. And so I hope. First of all, I hope that in this talk I did now, I might convince you to sign up for this research group. Even if I don't, I hope to teach you something cool and interesting and give you some idea of what is going on. The topic is, roughly speaking, something called Morse Theory, which is a subset of differential topology. And topology is a kind of geometry. Well, it's a subset of topology, which is a subset of geometry. Some people don't like thinking of topology as a subset of geometry, but anyway, the idea is, so what is geometry studies things in space, whatever space means, different shapes and so on. And then of course you want to say, well, when should I think of two things as being this? Anytime you want to study something in math, the first thing you want to ask is what does it mean for things to be the same, right? So typically in Euclidean geometry, things are the same if you can move it on a piece of paper. If you draw an equilateral triangle of side length 3 here and side length 3 there, that you consider them to be the same. Okay, but in topology, you look at much more subtle sort of features of shapes, and in particular, you look at features that don't have anything to do with length, angle, measure, and so on. And so, a typical example in topology, a square and a triangle are considered to be different. But if you allow yourself to bend or deform things, then the square and the triangle, these are not equal here, and the square and the triangle would be equivalent in topology. It would be equivalent to a circle because you could bend or deform one, but none of those are equal to, say, for example, a figure 8. There's no way you can deform or bend a figure 8 to make it. So this is just very quick what's going on with topology. And then we're going to be talking mostly about surfaces. So again, in geometry, for example, a round sphere is very different from, say, a lima bean type shape, for example. Well, actually, a small sphere and a big sphere are different in geometry as well. But you can talk about curvature and so on. This has, so if I'm thinking of these as surfaces on R3, there's you know, there's no isometry of R3, nothing that preserves length and angle, it'll take this to this, but in topology you consider them to be the same. And however, these would both be very different from, say, the surface of a donut, and that, and again, would be very different from, say, the surface of two donuts smushed together. I'm going to draw lots of surfaces, and surfaces, I'm thinking of, you know, the skin of something, right? So this is, you can think of, when I say sphere, I mean the set of points distance 1 from the origin, not the set of points distance less than or equal to 1 from the origin. That's a ball. Okay, so that, we're clear on that distinction. And so in general, I'm going to draw something, I mean just the skin of the object. Okay, okay.
So hollow sphere.
Yeah, hollow sphere. Yeah. Call it by, yeah. And yeah, so a donut where some worm got in and ate all the good stuff out. Okay. Now differential topology, differential means take derivatives, means do calculus. So the question is, how can we do some calculus to try and think about topological problems? Okay, so differential topology just means we're going to do topology, we're going to study shapes and so on up to some kind of equivalence, but we're going to all it means is we're going to use calculus. And Morse theory is uses calculus in a very particular way here. Morse theory is going to use calculus, well, we've got the surfaces, it's going to use, what Morse theory is going to use is the following 3 things from calculus, from multivariable calculus, which you may remember. Classification of critical points. I will remind you of that. Well, first of all, critical points, period. What does that mean? That means points where some derivative goes to 0, right? And so, for example, and in fact, I'm going to zoom in on, we're probably for most of the talk, I'm not even going to look at nice closed surfaces like this. I'm going to look at very simple kind of surfaces. We take a graph of a function of 2 variables. Okay, so an example of kinds of surfaces we might think about is, say, z equals f of xy. X of y, some smooth function graphic, you get some landscape. And so then you can take the critical points of this function f, and you might remember from classification, well, there can be actually all kinds of critical points, but typically you forget about that and you say, well, in any problem you're given in the homework book, the critical points are either maxima, minima, or saddles. Okay, so, and the reason that's the only ones that are, well, then you might see a few that are not, but you don't spend much time on it. But we'll talk about this. Try to keep, this is my overview of the talk. Okay, so I'm going to go back into a lot of these things in more detail, but maximum. Yeah. Saddles. So if you don't understand something now, we'll have a second pass at all of this. And then also level sets. Well, once again, level sets means, actually, this is all specialized into this case, z equals a function of x, y. So level sets would be, take z equals to some constant, right? And then you've got the surface in R3, you look at z equals constant, that's going to slice across the surface and get out some kind of one-dimensional thing on that surface. And then the maybe most fancy level sets, actually, in some sense, that's not even calculus, right? You've just got a function of several variables, you set it equal to 3, and you solve. You got a function, x squared plus y cubed, you could have the function z equals x squared plus y cubed. We'll actually talk about that function shortly. And then a level set would be, I graph z equals x squared plus y cubed, then the level set would be, look at the set of points where x squared plus y cubed equals 3. That's not even calculus, that's just algebra solving that. It's trying to find some way to graph that. But then the most sophisticated bit of calculus we're going to do is gradient flow lines. So you might remember the gradient vector field of a function. It's just, as you're calculating, it's just the vector, which is the partial of f with respect to x, comma the partial of f with respect to y. But the nice thing about that function is it points always perpendicular to the level sets. And in particular, you can think of it on the surface as telling you, well, actually, the way I think of it is minus the gradient tells you the direction water would flow if you poured it on the surface. Okay? Everyone's seen that sort of analogy for a gradient vector field before. So the gradient vector field is the direction water flows. The gradient flow line, well, if you have, the other thing you might, then this is actually differential equations, right? If you have a vector field and you want to find starting point and flow along that vector field, you're solving a differential equation. You're looking for functions x of t, y of t, so their derivatives are equal to the gradient vector field, and that's exactly finding the path that water would flow. So these are the ingredients that this is the part of calculus that we would use in studying, in using calculus to study topology. Okay. Now I've been talking about surfaces, and I will talk about surfaces almost exclusively today. And in the research group we'll almost exclusively work on surfaces. But all of this works in higher dimensions. It's interesting to think about higher dimensional saddles, maxima, minima, and so on. But we will try and keep it kind of focused on the surface situation. And again, the other thing I said is I'm going to focus on this picture. Notice that if I draw, for example, even just a sphere cannot be written as z equals a function of x and y, right? It can be written x squared plus y squared plus z squared equals 1, but of course if you want to write it as z equals, you've got to have plus or minus the square root 1 minus x squared plus y squared, so you have two sheets, so even worse things happen for a torus like this, right? But I will think a little bit about surfaces embedded in that more complicated surfaces. Okay, so now I think I want to erase the board and start. That was the overview, now we're just trying to start from scratch. Oh, well, I should tell you what the output I expect from the research group is. What I want to do is sort of think about, what I'll spend most of today talking about is this package of sort of things you can look at when you're thinking about surfaces. I'll try to give some examples. And what I want to focus on in the research group is coming up with visualizations of these three sort of bits of data associated with surface or a graphic function. We'll do sort of qualitative analyses first, so that means we're just going to draw pictures and sort of think without any calculations what things should look like. And then we want to do like hardcore computation. And I mean computation with a computer, because sometimes these differential equations we can't solve with standard techniques, and we use numerical integration methods. We'll sort of divide up the labor as to who's got what skills coming in, and then we want to make pictures of it. We want to make pictures of surfaces, critical points, flow line, gradient flow lines going up and down between critical points, and we want to animate that. We want to see, as I start wiggling the surface around according to certain ways, so there's going to be a time parameter, how do all those things change? And I have sort of a whole slew of different cases that I'm interested in doing, and the sense in which it is research is there may be people out there who have the same kind of qualitative pictures that we already, in their minds, that we already know or understand, but I haven't seen any decent, animations of any of this out there, the ideas that I have. So I think there's, in some sense, it's, well, when you're trying to, let me give you one example to show you where subtlety comes in. I'll give you two particular examples. One is, when you're doing first year calculus, and maybe you use a graphing calculator, and you've got some polynomial, and it's got an x to the fifth and an x squared, and you're supposed to use your graphing calculator to understand what this polynomial looks like. The x to the fifth, you might remember, dominates the behavior so much that in most windows, if you try to pick some nice window, it just looks like x to the fifth because x to the fifth gets so big so quickly that you never see any of the x squared behavior. You never see the little, the little x squared just makes little tiny bumps. So there's a lot of subtlety in making nice pictures that you have to think about carefully. Another example, so we're going to have polynomial functions where we have to be careful to think about terms that are very high order. We want to see behavior that's low order and that sort of thing. Another thing is I'm going to be interested in, I'll talk about this example more later, but I'm going to be interested in flow lines that go from a critical point to a critical point. Now, I'll give you an example of that later, but for the moment, let's just think about whether that makes any sense. What's the gradient vector field at a critical point? Saying that z equals f of x, y. What is grad f at a critical point? 0. Okay? So suppose you start at a critical point and start flowing along the vector field. Where do you go? Nowhere. Now I want to study flow lines that go from one critical point to another. Well, I'll give you examples where you see what I mean, but you see right away that that's computationally kind of a stupid thing to say. I want flow lines that connect critical. What it really means is that I want flow lines with the property that, you know, they're parametrized curves, with the property that the limit as t goes to infinity of one flow line is one critical point, and as t goes to minus infinity is the other critical point. And now how to implement that on a computer takes some genuine thinking and research. It's out-of-the-box thinking, not just sort of, it's not just simple plug and shell or something. We've got to think how you're going to find those flow lines, how you're going to find the ones that go in, and then if you start perturbing things, so there's that. Let me now start doing something. So I want to remind you of this critical points, level sets, gradient flow lines. But let's start again. Let's kind of start qualitatively, and then do some more explicit examples. Oh, and then the other question you might have in the back of your mind is, well, okay, how much computational skills would I need to do this? My general attitude is that smart people can figure out most of what they need to know about computers pretty quickly, and shouldn't be intimidated by computers. I mean, that's not to trivialize computer science so much, but in the sense that computer science I plan to use is not subtle computer science, right? Subtle computer science is deep. This is just like using some tools that are not that hard. There's lots of prepackaged stuff. You will have to write some code of some sort, but if you've never written any kind of code and you're super intimidated, that might be a problem. But on the other hand, I think even in that situation, you could get over that hurdle. It's not really, computers aren't really that hard. But you can talk to me if you have a concern. If you're interested and you have a concern about it, you can talk to me. Okay, so let me start with this sort of this is sort of a standard example in Morse theory. I'm going to think about a surface. I told you I would focus on surfaces of the form z equals f of x, y. Right now, I'm not going to do that. The standard example is going to be actually, let me start with a sphere. This is standard. Some standard examples. Okay. So I'm going to think about this sphere as a subset of R3. I'm going to call it sigma, stands for surface. And then I want to think about the function from that to R, which is projection onto the z-axis. There's the z-axis. So this is a function f. So f goes from sigma to R. And that's, f is the height function. Okay, so the height of this is 1, the height of this is minus 1, right? How many critical points are there? Just to make sure we're all on the same page. There are 2 critical points, right? There's a maximum and a minimum. Minimum, maximum. Okay. And the gradient, the level sets are parallel circles, right? Stop me. My lecturing style depends upon people stopping me if they don't understand. So stop me if you don't understand. So, and then the gradient, so that's the level sets, and then these are the gradient vector fields perpendicular to those, just go straight down. Right away, here's an example of a flow line that goes from one critical point to another, right? The flow line from here down to there, that's a flow line for the gradient vector field. And now, this flow line has finite length, but if you think of it as a flow for a vector field, you should remember that the gradient vector is, I'm in a bad habit of drawing minus grad f. And I say grad f, because I always think of downward flow. Grad f always actually points up, but so this is minus gradient. And so the gradient vector field gets shorter and shorter and shorter because the 0 at the top and 0 at the bottom. So that means if you start, say, at the equator, if you flow forward, it takes you infinite time to reach here. And if you flow backwards in time, it takes you infinite time to reach back there. So this is precisely that example. This flow line never actually reaches here, which is not really what water does, of course. Yes?
So I guess one other thing that ties into this, there's definitely not a unique way to flow from the max to the min. You could flow down pretty much any side of this sphere.
Exactly. That's also a very good point. In this case, there are many different flow lines from this maximum to this min. Okay, now let's start wiggling this sphere around. Let's start nudging it and pushing it. And I want to do it in the following way. I want to sort of, well, obviously it's a little bit of nudging to get it. Let's go to the Lima beam situation. Right? Now, and then, just give you a little perspective by drawing a few, well, yeah, just so I think you understand what I've tried to draw. How many critical points are there now? 4? Okay. Okay, so minimum, 2 maxima, and a 4 critical points. And now I've actually already, what I just drew there was a level set. I mean, not a level set, a flow line, 2 flow lines, right? This one there, and there's also a flow line going back. And this is a case where there are exactly 2 flow lines from here to there and no more. No, it's false state, okay? There, yeah, that's actually confusing itself. I stand by that statement. There are exactly 2 flow lines from here down to there and no more. You might say, what about a flow line that goes this way? Well, there isn't a flow line that goes this way. If we want to look closely at that saddle, what do flow lines nearby do? Well, there's this flow line as well, comes down. A nearby flow line sort of goes down, gets really close, and then scoots off like that. So this is sort of like, this is what water, so if water was flowing down and hit that saddle, and then zoom off to one side or the other. Okay. And then this. And also, what do level sets look like? Here they're just sort of look like circles, but at some point we get the level set passing through this critical point. What does it look like? We've actually already had it on the board. It's this A. Go ahead. It's an 8. It's a figure 8. Anyone not see that this level set goes right through there? It's a figure 8. Got that? So what happens is this level set down here, which is a circle, we want to sort of follow it back up. It starts as a circle, and what happens to it? I start to see sort of a pinching happening, right? 2 points coming together, and then I've got this figure 8, and then what do I have? What's the level set up here? Pairs of circles, right? And this one pinches off to a point, and this one keeps going a little longer and pinches off. All right. Now I want you to notice something, which is actually a theorem, but this is not a proof of that theorem, which is that the number of maxima minus the number of saddles plus the number of minima in both these cases is what? 2. Okay. It turns out that for a sphere, it will always be 2, no matter how you draw it. Unless you're in some kind of weird cases. Well, unless you're in some weird cases where you don't. Let me draw a weird case for you. By the way, who else has seen? Well, first of all, how many people have seen this fact before? Okay. How many people have seen something else, or I've got something minus something plus something equals 2? There's something called Euler's formula for polyhedra. And it says if you take any old polyhedron, like icosahedron, dodecahedron, cube, and you count the number of vertices and the number of edges and the number of faces, and you do vertices minus edges plus faces, you always get 2 as well. It's the same fact. And, that's beautiful topology. Actually, that's a good example of, this is differential topology, right? These are obtained from calculus. The other thing I said, that counting vertices, edges, and faces is what is often called combinatorial topology. So you're sort of building something out of, flat pieces stuck together in some combinatorial way. And this is a great example of sort of interpolating calculus and combinatorics there. we'll do some other surfaces shortly, but let me show you something that, so what's intermediate between these two? At what point does a change happen? And then I suddenly get an extra, somehow I got an extra max and an extra sal. There's an intermediate point where we have something like this. Okay? And how many critical, so this is supposed to be leveling off right here. How many critical points do you have there? You just, well, you actually just, well, I want it to level off just barely. What I want the profile here to look like? I want the profile here to look like the y equals x cubed graph. Just load it there. So the y equals x cubed graph, remember, tapers off like that. And that's your standard critical point of a function of one variable, which is sort of, but its second derivative is also 0. There's something sort of degenerate about it. Most critical points are going to be y equals x squared, and the second derivative is not 0. This is sort of first and second derivative 0 at the same time. So here, your answer depends upon what I meant by this drawing, right? But I claim what I mean by this drawing is this is leveling off to just one critical point. I'm starting to go from here to there by sort of putting my hand in here and pushing up until I get this other bump. And the first time I get a new critical point, I actually get a single critical point. I have 3 critical points here. This is a min, this is a max, and this is just plain old bad. Bad from the point of calculating something. You could, but what it really is it's the birth of a pair of nice critical points, and it has to pass through something. This is an example of the kind of phenomenon we're going to be thinking about as well. And it's worth thinking about here, for example, you look at the the flow lines from this point, and sort of all these flow lines go down and then back, and then up here you've got flow lines that sort of do this. And then the level sets here. Actually, here's a test for your intuition. What do you think the level set right there looks like? Teardrop. Very good.
Yeah.
It's a teardrop. It's like this. If I were to look at it head down. That's the level set there. One way you can see that it's got the teardrop down is I'm going to forget about it. And I haven't done anything interesting in the southern hemisphere, so let's just look in the northern hemisphere and just draw. Let's now draw contour maps of these 3 different situations. So I'm going to draw everything down, and ignoring the bottom half. On the left, we saw contours. Like that. I guess they should be, if I really want to do it right, they should be more bunched together near the equator, right? Something like that. And that's sort of that's the level sets looking down the sphere there. And then after, I should have done those, I should have left a gap here and put this on the right. So it goes, that's step 1, this is intermediate, this is final, right? So I'll try to do the final over here. Looking down at it, we see this stuff out here, we see a figure 8 somewhere in the middle. And then we see this. Well, you can see it contour. Any question of what I've drawn here? If you don't know what I've drawn here, then we're going to have trouble later. So, got this picture? This is how this picture comes from that. And so intermediate, this is the one that's being created, right? This and this pair, so intermediate, when you have, what happens is that this stuff gets pinched down, 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 and you've got to have, you're going to have this teardrop level set. I'm being a topologist, so I'm not being too careful about how bunched together they are. But the point is that because this stuff is got 2 horizontal tangents, and if you make this part smaller and smaller and smaller, you keep having those 2 horizontal tangents. That's sort of a qualitative proof as to why you need to have this teardrop, because in the limit, you know, these two horizontal tangents have to limit on something that's got a curve that's got a horizontal tangent that's pinched. Okay. Okay. That's the. Let me do one example for torus. And then we start doing some more careful. So, another standard example is I'm going to put a donut standard on its end. Sorry. Those are some level sets there. I've got how many critical points now? 4. Minimum, saddle, maximum. Okay. The level set that passes through this critical point is another figure 8, and there's a figure 8 here, and then sort of you have a circle here that slowly hinges. I'll draw much more there. We'll complicate the picture. Maybe you know what's going on. I'll do one more. Okay. What about flow lines? Let's see, there, for example, out here, that's the flow line. All the way down, there are lots of flow lines. But at some point you get a flow line that runs smack into that critical point, and a flow line on the back that runs smack to that critical point. And then on the back side. It's here. Here you've got a flow line from this critical point down, and a flow line from that critical point down. What about from this critical point to this critical point? Yeah, it sort of looks like there should be one from here down to there, and one from here down to there as well. Right? Now, here's another example of the kind of things changing in time that I want to be focusing on next semester. This is actually a very non-generic phenomenon, in the sense that you have to have the torus perfectly upright, the way I've drawn it, for this to happen, for water to flow from here right down to there. If you tilt the torus just a little bit, water from this saddle here going downward south. When you think of this as a saddle on the inside, right? So sort of water, you're in the torus pouring, you're inside the torus pouring water here, right? And water's going to come down, and it's most likely going to miss this thing, right? So if you think about just, you know, you've got this point you're trying to hit, right? You've got these two lines coming down, and chances are they're not going to hit that point, right? When you've got lots and lots of lines coming down, chances are one of them's going to hit the point, right? But here you've got most of them are not going to hit that point, and so if you tilt it just a little bit, you're going to have the situation that flow lines come down and go around the back, and actually those flow lines aren't there. Now I'm just going to get sloppy with my pictures and just talk more, but you're going to see these flow lines in the back come and go all the way to this flow. And if you tilt it forward, you're going to have the flow lines come forward this side of the critical point. You can sort of tilt it back and angle it, and you can have flow lines go one side or the other. There's a lot of different ways you could orient this torus in here and see flow lines go different ways. Now, I just said I'm going to get sloppy with my pictures. The reason I'm going to get sloppy with my pictures is because I haven't run this Introductory VIGRE Research Group yet, and you guys haven't produced the computer animations that I want that I need in order to give this talk. Right? You get the picture? You understand what I'm saying? That's what I need you for. But again, this is an example of the kind of qualitative analysis we do before we then try and create beautiful pictures that communicate effectively. Okay, and there's all sorts of other things you can think about with this. You can start putting your hands in here, bumping it out, and creating another pair of saddle and maximum. Here, if you count, it turns out for a torus, if you count the number of max minus number of saddles plus numbers of mins, you always get 0. And if you start fiddling around with things, you always get 0. Actually, the real proof that this number is constant is saying that if you have one height, if you have a torus drawn one way and you have a torus drawn another way, and then you start just, you know, deforming the one to the other, exactly what happens is through that deformation you have locally this phenomenon happen. You have the only thing that can happen is a pair of critical points is born and maybe dies. And so anytime a pair is born, it's either a minimum and a saddle, which contributes nothing to this sum, right? Or it's a saddle and a maximum, which contributes nothing to the sum. So the sum stays constant, and that's the proof. Of course, you need to believe what I said, that that's the only thing that can happen. And that's not true. What I mean is generically that's the only thing that happens. Which means if you sort of take, if you wiggle it, if you wiggle one to another, if you perturb one to the other, you might do some kind of really weird, not very generic perturbation, but you can wiggle the, so this is the kind of argument we talked about. You have a path of functions on a torus, a one-parameter function family that's time for changing the height function on the torus every time looking at the critical points. Now, that path, I can change that path with another parameter, so you sort of have two time parameters, s and t. And the claim is that for any path from one nice function to another nice function, you can wiggle that path with another parameter to get a path in which the only thing that happens is births and deaths of cancer pairs of critical points. And so there will also be some cases where I want to investigate what are. The first thing I said is we want to make movies of these things moving around. That means one time parameter. I also want to investigate in this research group some two-parameter families of functions. So let me now get much more explicit and write down, and let me move to the z equals f of x, y situation and talk about some particular cases. So let's take z equals. Let me just throw my figure one right at it. I'll do it a funny way first, and then I'll write it as the real part of x plus iy cubed. Okay, so I'm suddenly bringing in complex numbers. What I really want to do is, in some sense, what I'm really interested in is the map from the complex numbers to the complex numbers, which is cubing. Anyone have any intuition about that map? Yeah.
Takes your space. Yeah, so you're
Well, tell me, what is it? Okay, let's start. What does it do to 0? I'm looking at the complex map z goes to z. What does it do to 0, first of all? 0 goes to 0. What does it do to the unit circle?
It rotates it.
E to the I theta, so we know 0 goes to 0. Okay. E to the I theta goes to E to the I theta cubed, which is the same as E to the I 3 theta. So rotating is not, I don't think that's what you need. Rotate means, let's just take the whole thing, just like this.
We'll cover it 3 times.
yeah.
So the unit circle in the complex plane is, if here, when theta goes from 0 to 2 pi, you go around the unit circle. Okay. Now, the image of 0 to 2 pi becomes 0 to 6 pi. So the unit circle gets wrapped around itself 3 times, precisely, right? So that's sort of, that's a picture somehow. The origin is fixed, and everything else is wrapped, and then of course, parallel circles, concentric circles, more or less do the same thing, except they also get expanded. That's something like that. And so it gets wrapped, the plane gets wrapped around itself. It's very hard to really visualize this, but it sounds like a picture. And now I just want to look at one part of that. I mean, you might then look at the imaginary part as well, so it's split it out one by one. But this is a function, but we can just compute it, of course. X plus iy cubed, you want to know the real part, so you want to know the part with no i's and the part with I squared. And so if you remember, you're going to have x cubed, and you're going to have plus 3 I squared y. Sorry, what am I doing? 3x, I'll write it this way. 3 times this times that squared. Right. 3 times this squared y. I y squared. In other words, there's 2 other terms in the trinomial, right? Factor when you expand out cubing. and the other terms have I or I cubed in them, which is imaginary. So the real part is just this, that's x cubed minus 3xy squared. This is actually a famous function that has all sorts of interesting features. One interesting feature it has, well, it has a critical point at the origin. So you can just compute for f, and it's going to be 3x squared. I'm taking the derivative with respect to x first, so 3x squared minus y squared, thank you. And comma, the derivative with respect to y, so that's minus 6y. And notice that that's 0 when x and y are both 0 only. So this is the so critical point 0. Now the question is, what kind of critical point is it? Saddle, minimum, or maximum? The answer is none. It is what is famously called this surface is famously called the monkey saddle. And you may have seen this before in torus, perhaps. It's a nice example. It's one of the nicest examples of a critical point that doesn't fit into that package, max, min, or saddles. And it rather than try to draw this surface, I'm going to try to draw the contour now. Right? So this is just I'm just going to draw something in the xy plane, and I'm not going to be too. We don't have time to do the calculation. I claim that the level set passing through the set of points. I claim that if I set this function equal to 0 and solve for x and y, I get three lines passing through. I claim that is f of x z equals 0. And then if I take z equals something slightly larger than 0, I get these things. And if I take z equals something even larger than that, I get something like this. Right. And then if I take, so this is sort of, I'm going to write pluses here. This is where z takes positive values. And then when z takes negative values, I get something like this. Now again, we can, in the group, we would have time to, one of the first things we should do is sort of see qualitatively why that's what's going on. Now, as a contour, as a landscape you might come upon, what this means is if you're standing here, you've got 3 directions you can go down and 3 directions you can go up. So you've got 3 mountain peaks nearby you and 3 valleys to go down. So it's called a monkey saddle because it's got, the monkey's got 2 legs and a tail. As opposed to a person that's just got 2 legs. So this is not one of the standard critical points that we can think about in Morse theory. One of the basic facts about Morse theory, which we will prove that is useful, but you use this sort of in order to calculate this and it's believable, is that the critical points that we consider, minimum, maximum, saddles, are the only generic ones. Any other function that has some other kind of critical point, if you perturb it a little bit, that critical point should somehow break up into minima, maxima, and/or saddles. So something should happen. So what I'm interested in is taking this funny critical point. You can easily sort of figure out what the gradient flow line should look like. These are down, this is going down, this is coming, I'm drawing the downhill dividing. Starting like that. So that's I'm not going to draw them all in there. So now let's think, how might you try to perturb this function? This is what I'm interested in now, is making. One thing I want to do is think about ways to make. We may actually Eddie may pull this one off over the summer. I'm not sure if he's doing that this summer or not. But I've got lots of other examples. But this is a nice sort of starting. So here's something you want to visualize. Now the first thing is to try and visualize this surface. So I've got this point here, and I've got down, 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 up, 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 3 different directions. Okay, now I'm going to. One way I'm going to try to, I want to break up. This is like a bunch of critical points kind of come together in some way. So I want to try to break it up. So first of all, if you look, I said it was down there and up here. And So it goes down, up. Now what I want to do is put my hand right here, and the surface is going down to either side. And then I want to just lift a little bit. I don't know if you can see this or not. I've got this, where am I putting my hand? I'm running my hand right, let's say, right along this line. Okay? So the surface is, this line is just going down all the way. Except it sort of somehow levels off right in the middle, right? Because this is a critical point, so the tangents are all zero. So somehow right along this line, it goes down, it levels off a little bit, and goes down again. And I want to just put my hand under there and lift a little bit so that critical point breaks up. And I claim that what you're going to get is you're going to get two saddles out of this. You're going to get, this critical point will break up into, now I'm going to do it, let me try to draw the, so here's how I want to think about this. I'm going to draw the picture of the level sets again, just because that picture has got too much on it. Okay, remember, plus, minus. And what I want to do is I want to create, I'm trying to illustrate for you the kind of qualitative analysis we can do here. I want to imagine something which looks pretty much the same on the outside, okay? But something has changed in here. I want this to break, in here I want things to break up into two little, so that, maybe I should have reminded you from the very beginning, the contour picture for a saddle, right, looks like an ordinary harness saddle. Okay, so can I do this? So let me start by sort of drawing what I have on the outside. And I want to try to fill this picture in slightly differently in the middle. So notice that what I can do here is I can just simply connect this line across to there, and this line across to there, and come straight across like that. And now I've got two nice saddles. Let's just check pluses and minuses. So again, this region should have been down, this is up, this is down, this is up, as it always was. All of this is up, down, down. So that, I claim, is what happens when you put your hand in there and just push out a little bit. The other thing I want, so the first thing you can imagine is this is all the way I got this picture is I just took this picture and sort of erased the middle and tried to fill it in with some contour level for where the only kinds of critical points I see are this. Right? And it just works. Right? You're lucky you're able to fill it in. And then I claim there's actually this visualization. Once again, after next semester we'll have much nicer pictures to show, right? So now of course you could have done this in three different ways. You could have done it here, right? Or you could have done it here. And actually what you could have done is put your arm under it in the middle, and then you could have spun your arm around as you go and sort of perturb what I claim is there are three different ways to perturb this, but they're actually connected by a circle's worth of perturbations. So I want to think of one thing I want to see is a movie where I go from this to this thing rotating to the thing rotating, but not just by rotating, by sort of seeing critical points come together and move around, which is actually computed from this. And it's a movie that goes in a loop, because time goes in a loop, because you go around the circle and you come back. Okay, I'm going to stop in 1 minute. So let me just tell you the other thing you can do with the monkey saddle to break this up instead is you could just put right underneath the monkey saddle, just put your fist there and just push up. What's that going to do? That's going to, I claim, actually let's just do it the easy way. Let's just do that by erasing, okay? Okay, I just pushed up here, so now I'm just going to have maximum. Okay. How in the world can that reconcile with what's coming in? I claim that the only way to do that, to reconcile this picture, is to have, do this, I want to have 3 critical points around here. So plus, minus, right, I need to have so if you have something like this, yeah, this is what you do. And then that's going to go to no, I didn't plan it right. There's another way to do it. So this is again an example. So you'll probably figure this out 5 minutes after this thing. So let's leave that as a question which I didn't plan properly, which is what do you see if you bump up or if you bump down? And then finally, what you can think of is that turns out that there's actually so you can push up, you can push down, you can put your hand under and twist around, right? So you've got a circle's worth of things, and you've also got an up and a down. Actually, what turns out is that all fits together to make a sphere's worth of different ways in which you can perturb this nice monkey set. Now, that's an example of something that a handful of people might understand in the world, sort of, but I've never seen any kind of picture. You know, who knows what we could do. Of course, it's hard to make an animation in which time is moving through a sphere, right? In which you've got 2 dimensions of time. But that part of the research also is having interesting ways to present that information. You could have some GUI where you've got a little sphere, you could point out on it, and it shows this particular function. Anyway, I should stop. There's refreshments, I believe. We'll take some questions as well. Yeah.
So our initial saddle is taken by taking the real part of x plus iy squared, right?
That's correct, yeah.
So do you have more general behavior where you get fundamentally different, where you sort of divided things up into 8 sectors when you take x plus iy
Absolutely,
to the
yes.
4?
Yes, yes. I mean, that's also that's a perfectly natural thing for us to try and make pictures of as well. Cubed is the first degenerate case that you get. There's lots of interesting behavior. And then the other thing is when you start having quadratics, quartics, right, to the power of 4, then you start having more different ways in which you can perturb it as well. So here, in some sense, there's 2 dimensions worth of ways you can perturb it, depending on which direction. So you've got an equator, and you've got up and down. When you get to 4, there's more dimensions to perturb it as well. Anything else?